Let's continue our discussion on probabilities. In the previous video, we talked about some terminologies, some sample space, events, mutually exclusive, probability, and things like those. We went through a couple of examples, one finite, one infinite. We went through some properties of probabilities. Probability must be between 0 and 1, 0 and 100% if you prefer percentages. Probability of an empty event is 0. Probability of anything possible is 1. And if you have two mutually exclusive probabilities, probability of that disjoint union is the sum of the probabilities. Using that and this one together, you can deduce the next property. Probability of an event plus the probability of its complement event turns out to be the probability of whole space, which is 1. Consequently, flipping one from the other, we get this computation. Probability of the complement is 1 minus the probability of the original. For example, how do you calculate the probability of getting anything other than 1 when you roll a die? You can count and get 5, 6, or you can calculate 1 minus 1/6. Now, let's talk about conditional probability. What is the conditional probability? When you restrict the sample space by a certain condition, then you get, of course, different probability. And that kind of probability is called conditional probability. Here is rather formidable definition given in terms of set theory. The conditional probability of an event A given the event B is defined by, well, probability of the intersection over the probability of B. We'll talk about this set theoretical expression at the end of this video. First, let's get ourselves comfortable with the concept of conditional probability using an example that we have already seen before. Here, let's begin with some data table that we discussed in chapter 3. We have 30 students, names are not that important, and gender is there, the majors are there. Counting their numbers, we get this contingency table. And with this contingency table, we can answer some questions. If one student is selected at random, what is the probability that the selected student is a female student majoring in liberal arts? The total here is, well, the total, 30. There are 30 students. And one student is selected at random out of this college. Oh, excuse me, not out of this college, excuse me, out of this sample of 30 students. So what is the probability that selected student is a female student majoring in liberal arts? There's 6 where my mouse is. So the probability is 6 over 30th, which is 0.2. Female and liberal arts. It's easy to calculate and easy to understand. Now let's consider a couple of conditional probabilities. We're going to concentrate upon female students majoring in liberal arts, but different conditions. If the selected student is a female, so we have to consider within female students alone for part B. So in other words, we're discussing different sample space. Instead of entire 30, we're concentrated upon just 12 female students. Male students, those are totally out of consideration here because this condition said if the selected student is female. So new sample space, so division by 12 instead of 30. What is the probability that the selected student, whom we know as female, is majoring in liberal arts? Well, here it is, 6 divided by 12 this time. In decimal, 0.5. See the difference? We are changing the sample space by condition. If one student is selected at random, okay, random selection, but no further condition is given. Out of where? It's not given, which means you have to take from entire 30. This time there's a condition. If the selected student is a female, then I'm not considering any male students. We are considering different sample space of total 12 female students. Let's take another exercise. Let's do something similar. If the selected student is a liberal arts major, very similar problem, except that we have different condition. If the selected student is a liberal arts major, what is the probability that the selected student is female? So what's the denominator this time? What's the denominator this time? It should be 11. That's the condition. That's the new sample space. Instead of 30, not 12, this time we are focusing upon a condition, upon a major. So total is 11. So what do you get? We have 6 over 11. Approximately we get this decimal. These kind of things are called conditional probabilities. As a matter of fact, in this exercise, we have further probabilities repeating the same to each category. We have all these probabilities. Select what's the probability that the selected student is a male technology major. About 23%, because it's 7 over 30 and histograms are given. And then you can do the same thing with the other condition. If the selected student is male, what is the probability that he is majoring in technology? We can answer those kind of questions. And then selected student is male, so the denominator will be 18, and you have to consider 7 over 18, kind of like that. You can change this problem into variety of settings. Okay, I think that was enough exercise on the basics of the concept of conditional probability. Basically, changing the sample space. But then again, what is this? What is this horrendous set theoretical notation? What does it mean? Is it really necessary? Very sadly, yes, it is absolutely necessary. So we cannot get away from it. So let's discuss this. Let's discuss the same thing using the same example, except that this time let us focus upon the set theoretical expression. And let me copy this down here so that I can always see this in the same viewing window. Okay, let's go back. If one student is selected at random, what is the probability that the selected student is a female student majoring in liberal arts? Here it is, female and liberal arts at the same time. So 6/30, here we go. And this is a problem we did before. Liberal arts, if the selected student is female, so that's the condition. Given that condition, what is the probability that she is majoring in liberal arts? So we changed the sample space and then got 6 over 12, 50%. But what if we use this set theoretical expression? What we have? We're going to get something like this. Another way to view the same thing is, what is the probability of the intersection? Selected student is female and she is liberal arts major. There are 6 such students, as you have done in part A. So that goes to the numerator, 6/30. Now what about the denominator? Probability of the condition. Condition? Well, female. So 12 female students out of total 30. So the condition will be 12/30. The probability of the condition, the denominator will be 12/30. After simplification, you get 6/12. But you can view it in terms of set theoretical expression as we see over here. Tricky? Well, I've taught this course many times, but always students struggled right here, and some vocally complain that why do we have to do this in 2 different ways, where one is significantly easier and the other is significantly harder. As a matter of fact, that question will be answered a couple of sections later when we do Bayesian analysis and things like those. Yes, it is necessary that we do both. Well, we have some time, so let's repeat this exercise. Let's go back to this. If the selected student is a liberal arts major, we are considering the other condition. What is the probability that the selected student is female? Let's use the set theoretical expression to answer the same question. What is the numerator? The probability that the selected student is female and liberal arts. Actually, we calculated. How about the denominator, the condition part? That should be the probability of getting a liberal arts major. In short, we have this kind of computation. Denominator is 11/30th because there are total 11 liberal arts majors. The new sample space gives you actually the probability of that new sample space. And then the numerator, as you saw before, is the probability of the intersection. And this is the set theoretical expression rewritten from here. This kind of thing is called the conditional probability. If you look at it in terms of contingency table, not very hard. If you look at it in terms of the set theoretical expression, it is hard. By the way, I have a little bit of time, so let me answer the question, why in the world we are doing this? Well, okay, let's answer that question. Here is. From this, you can flip the denominator to the other side, and you're going to get this identity. And what do we get? The probability of A and B is the probability of the condition times the conditional probability. As a matter of fact, it would have been a bit easier the other way around. It's okay, multiplication is commutative. This condition part works more or less like a denominator. And we have this multiplication rule. And this multiplication rule can be repeated. I don't want to get too advanced here, but this is basically where we are headed, and that's why we went through this set theoretical expression, which is significantly harder than the way we do it through contingency table. Of course, we are going to come back and do this in the other perspectives way back in section 4 of our notebook, when we have to deal with so-called multiplication rule and tree diagram, stochastic processes, and things like those.